Assalamualaikum everyone. My name is Muhaiminul Haque Prottoy. I am happy to be here today to present our research paper titled Deep Learning for Brain Tumor Detection, Unit Segmentation and Exception Classification with LoRa-Driven Synthetic Data Augmentation with paper ID 189. In introduction, first let's talk about the challenges when doctors look at MRI scans to find brain tumors. The process can be slow and can sometimes lead to mistakes. This can delay important treatments for patients. A major weakness when using AI for this task is something called class imbalance. This means our computer models don't have enough examples of rare diseases. Real-world medical data has many images of common tumors but very few of the rare types. This makes the AI good at finding common tumors but unreliable for the rare ones, which is where we need the most help. To solve this problem of not having enough data, we use a method called data augmentation. Traditional methods are simple, they just modify the images we already have, for example, by rotating or flipping them. This is just this is just fast, but it doesn't create any true new data. More advanced methods can create brand new artificial images. These are powerful but often require a lot of computing power and are expensive to use. This brings us to our three main goals for this project. First, we wanted to accurately find the outline of tumors using a model called UNIT. Second, we aim to correctly classify the tumors into four different types using a model called Xception. And most importantly, our main goal was to solve the data imbalance problem by using LoRa to create new artificial data for the rare tumor types. We choose our models very carefully for finding the tumor's location. UNIT is a top choice in the medical field. It has a special feature called skip connections that helps it to see both the big picture and the small details, which is perfect for drawing exact outlines. For identifying the tumor type, we choose Xception because it's both accurate and fast. It uses a small trick to do this calculation more efficiently, which makes it great choice for use in a real hospital. So how did we create high quality data without needing a supercomputer? The answer is a technique called LoRa. Training a huge AI model from the beginning is very expensive and slow. LoRa gives us a much more efficient way. Instead of retraining the entire model, it just adds very small trainable parts to it. Here's a simple way to think about it. Imagine an artist who can paint anything. To teach them a new specific style like painting a rare type of tumor, you don't send them back to art school. Instead, you just give them a small sticky note with a few instructions. The artist uses this note to learn the new style, but all their main skills stay the same. LoRa is like that sticky note. It's guard, a small smart guide for a very powerful model. In our project, the artist is a powerful model called Flux.1Dev. It has already learned about general shapes and textures from looking at billions of images. So here's how to use it. We take a few real MRI images of rare tumor and use them to train our small LoRa adapter. This adapter becomes our sticky note with instructions. Then we attach this trained adapter to the main images. The Flux model follows the instructions on the LoRa sticky note and produces hundreds of new realistic images of that specific rare tumor. This gives us the power of a huge model at a very low cost. We started with two datasets, one for finding the tumor and one for classifying it. We trained our UNIT model to find the tumor outlines. For classification part, we first tested our Xception model on a balanced dataset consisting of 500 images for each classes. Then, to copy a real-world problem, We created an imbalanced dataset by removing half of it. We then trained a LoRa adapter on the few remaining images and used it with Flux to create new artificial images. Finally, we added these new images to our dataset to make it balanced again, and we retrained our Xception model. We then tested how much better it performed. We repeated this process for all 4 classes. Here's the architecture of the unit segmentation model we used, and this is the exception classification model we used. And these are the equations for the matrices we used for evaluating the performance. Now for our results, our unit model was very successful at finding tumors, achieving a die score of 88.43%. As you can see from the images, the predicted outlines are very accurate. The artificial images we created with Flux and LoRa are high quality and look very realistic. Most importantly, our experiment showed a clear improvement. The graph showed when we removed data from one class, the model's peak accuracy went down. But after the adding of our new LoRa-generated images, the peak accuracy went right back up to its original high level. The tables show this in detail. On the original data, the model's F1 score was high, over 95%. When we removed the data for the glioma class, its score dropped all the way down to 92.15%. Our LoRa technique was the most effective at fixing this, bringing the score back up to 95.53%. Here are tables for other augmentation techniques where the metrics are comparatively lower than LoRa technique. The confusion matrix chart also show that the model made fewer mistakes after we added new LoRa data. We also compared our final model to other recent research projects. Our model improved with the LoRa data, is very competitive and achieved a final accuracy of 96.71%, which is higher than several other published models. This is the Gradio interface we created, and anyone can check out the link to use this. This technique can be used for much more than just brain tumors. The problem of not having enough data for rare diseases is common in all areas of medicine. This LoRa method could be used to create data for rare types of cancer, for rare diseases in children, or for uncommon eye diseases. It can help make AI more useful and reliable tool for doctors everywhere. Of course, our model has some limitations. We only used one type of MRI scan, and we used public datasets, not real data from a hospital. For our future work, we plan to include more types of MRI scans, explore newer AI models, and most importantly, work with hospitals to test our model on real patient data. In conclusion, we have built a successful system that is highly accurate at both finding and classifying brain tumors. Most importantly, we have shown that using LoRa to create artificial data is a powerful and low-cost way to solve the critical problem of data imbalance in medical imaging. We believe this work is a big step toward creating better AI tools to help doctors and improve patient care, especially for those with rare diseases. Thank you everyone for your time. You can ask me any question.